We're going to talk about graphing trig functions now. So previously we were just trying to learn what sine, cosine, and tangent ratios were. Now we're going to try and figure out what they look like as some sort of function and see if that makes any sense to us. So the first thing we're going to do is we're going to write down all of the sine and cosine ratios for each major angle, like a pi over 6, pi over 4, pi over 2, pi over 3, and all of those subsequent reference angles that go with that from 0 all the way to 2 pi. And so these are things that we should already kind of know. Notice that in the first quadrant, sine gets bigger as you move forward and cosine gets smaller. Notice that sine starts at 0 and cosine starts with 1. And then the sine values stay positive in the second quadrant because y is greater than 0 in the second quadrant, but cosine values are negative. Cosine values are getting more negative, like biggerly negative, I guess, and sine values are getting smaller, getting closer to 0. Then in the third quadrant, both things are negative. And in the fourth quadrant, the sine values are negative while the cosine values are now positive, and they just represent all the reference angles that we already kind of know. Couple things just to keep in mind that we may just want to point out when you look at sine and cosine, their pi over 4 reference angle, sine and cosine is actually the same measure. One of them is negative and one of them positive. Sometimes they have the same value, like at 5 pi over 4. But most of the time, they have root 2 over 2, at least in some sort of aspect there. And then another thing to keep in mind is that if you look at the pi over 6 and pi over 3 reference angles, um, when you look at sine of one of them and cosine of the other one, they should be the same pretty much. I mean, one of them in this case is negative and one's positive, but that's not always the case. But the main reason why that is because if we're just going back to basic old uh, triangles, the adjacent side and the opposite side of an angle, if I'm looking at this angle down here, uh, the opposite for one side is the adjacent for the other angle. And so when we flip 60 and 30 degrees, it should make sense that sine and cosine end up basically flipping spots there. So that's why the sine of 11 pi over 6 is the same thing as the cosine. Consider absolute value, like considering the negatives notwithstanding, the cosine of a pi over 3 reference angle. And then um, the sine and cosine of 11 pi over 6 are going to be different in that case because 30 and 60 end up basically trading spots. So anyway, that's stuff that we kind of already know. But if we're looking at graphing these things, it's kind of important to remember that if I'm graphing y equals sine of x, then theta becomes the x and sine of theta becomes the y. Because if I'm looking at y equals sine of x, the x is now the angle and the y now represents the ratio sine of x. Same thing if I'm doing y equals cosine of x. If I'm graphing that on an xy coordinate plane, that means that theta becomes the x, my angle is now the x, and cosine is now the y value. So these values are going to become what I have on my xy coordinate plane when I graph the functions. So that's one more distinction. So to graph sine, cosine, and tangent, I need to understand that there is a difference between looking at them as ratios on a unit circle and graphing their functions. So one thing that is important to understand the difference is that if I'm looking at sine, cosine, and tangent, notice that theta, in this case on the right side of my screen, is the angle, and x, y, and r are distances or lengths that end up making the ratio. So theta is the angle, x, y, and r form the ratios. So x and y in this case mean a little bit different things than they do in these functions that we're graphing, because I need to notice that over here, x is the angle and y is the entire ratio. So that means y is a number, x is an angle over in this part of the world. But when I'm looking at the unit circle, x, y, and r do not represent angles at all. Theta represents the angle, x, y, and r represent distances. So if I can be a little bit more visual with it, this represents y, this represents x, this represents r. Theta is this angle in here. And theta, being the angle, means that theta in this picture represents x on these graphs. So whatever theta was in our picture for the unit circle is going to be placed in the spot of x when I'm graphing these functions. And then y over r, whatever that ratio is, that is now going to represent the new y value over here in my sine graph. X over r, so whatever x divided by r is, that's now going to represent my new y value over here on the graph. So it's just one more way of making sure that we understand that theta and sine of theta, like the y value on the unit circle, does not represent the y value over here necessarily. Okay, those things, or on any circle in particular. So if I look at this triangle, we have now made the representations or relationships between what theta is and the new x over here, and then these ratios and what represents the new y. Now, I have taken the liberty to plot all of the points that appear to show up back here for sine and cosine. So I've plotted these points. So sine's graph looks something like this, at least when I plot the points. And then cosine's graph looks something like this. I can see if I type in y equals sine x, it kind of looks a lot like what I did, except it keeps going for a very long time. That's because if I have coterminal angles, they're going to give me the same ratio value. So if I have y equals this function, remember y was the ratio and x is the angle. So if I have x being 0 or 2 pi or 4 pi, then all of those are coterminal and I end up with the same value. What if I plot pi over 6 for the x, that's the angle. I know that the sine is 1/2. Right? Well, what if I have a coterminal angle, like 13 pi over 6? I should end up at 1/2 again. So notice what's happening is that this continues to go on and on forever. Okay. Likewise with cosine of x or tangent of x. Whoa, tangent of x looks crazy. We'll deal with that in a second. So sine or cosine, they kind of look like this. Now, what I'm going to do is I'm going to zoom in on the graph to exactly what we saw when I was graphing it. So I graphed one period. If I graphed one period of this and I look at y equals sine of x, it looks a lot like what the dots look like. So basically, in order to graph this, I would just connect the dots. And then I have a pretty good sketch of what sine of x looks like. Now, in order to graph sine of x, do I need to plot every single one of these points every time? No, I need to know what the general form looks like. So when x equals 0, y equals 0. When x equals pi over 2, we have 1. When x equals pi, we're down to y equals 0. 3 pi over 2 is a -1. And at 2 pi, we're back to 0. and then it would continue on forever. But we typically are only asked to graph one period, so I'm only graphing one period here. Cosine is likewise. So if I graph cosine, I would connect the dots, but I'm not going to be expected to actually draw all of these dots every time. So I want to try and make a relatively smooth curve. I'm doing it with a tablet, so it's a little bit harder, but I want to make a relatively smooth curve, and that should look a lot like this function here. So it starts up at 1, gets down to 0, and then at pi, it's down to -1. At 3 pi over 2, we're back at 0, and then at 2 pi, we kind of start our cycle again. And notice that this cycle continues forever and ever. Now, tangent is a little bit different. Tangent is sine over cosine. So if I put the sine values divided by the cosine values, and I took a little bit of liberty to do this on my own, but I also know certain really easy ones. Like, for example, at pi over 4, I have 1. So, like at pi over 4, I know that I have 1. And so on. So it looks something like this. Now we have these undefined values at negative pi over 2 and pi over 2. So these represent my y or my x values up here. And then these represent my y values down here. Notice that I don't have to put the x equals 0 on this line if I don't want. Now I can, but I'm just kind of putting x equals 0 right here for my own ease. So if I graph this function, I kind of have an awareness of what it looks like based on based on looking at the Desmos. So it looks like I have asymptotes at negative pi over 2, 3 pi over 2, 5 pi over 2, and so on. And my graph looks something like this. Now, why did I stop here? I stopped here because that was what I just did from 0 to 2 pi. But I don't have to stop there. I can keep going, and tangent's going to look something like this. And then at 5 pi over 2, I'm going to have another dotted line, something like that, at 5 pi over 2. So this is kind of what the tangent graph would look like. And that's kind of enough for tonight in order to think about what's going on. We will get back to this and talk about it more in class and talk about it in further videos about how to move these around and shift these. But this gives us a good idea as to where to start.